everyone and welcome back to Study Room. I hope that you all are doing well and the numbers are not bothering you much. So in the previous lecture we discussed about mensuration and how to calculate the perimeter and area of some of the well-known geometric shapes. In today's lecture, I'll be discussing with some of the important and special quadrilaterals. We'll learn how to calculate the area of those quadrilaterals and some other interesting stuff. So let's get started into the video. The first and the foremost special quadrilateral that we have over here is a rhombus. Now, before starting the area of the rhombus, I would like to discuss some of the important properties of the rhombus. So in a rhombus, all the sides are equal. So if this ABCD is a rhombus, I can see that all the sides AB, BC, CD and DA, they are equal. Another property is that the opposite sides are parallel in a rhombus. The diagonals of a rhombus, they bisect each other at right angles. This means that if we have this diagonal AC and BD, they will be bisecting each other, that is dividing each other into equal halves at right angles. That means the angle that will be formed over here is 90 degrees. Now talking about the area of the rhombus, let us first join this diagonal AC such that this diagonal divides this rhombus into two triangles, that is triangle ACD and triangle ABC. So the area of this rhombus will be equal to the area of this triangle ACD added up with the area of this triangle ABC. Let us calculate. So area of triangle ACD is half into the base of the triangle, that will be equal to AC, multiplied with the height of the triangle, which is equal to OD. Now, what about the area of triangle ABC? The area of the triangle ABC will follow the same formula, that is half multiplied with the base. The base over here is AC multiplied with the height, that is OB. Now from these two terms we will take half and AC common. So half and AC is taken outside and it is the common. So here we are left with OD from the first term and OB from the second term. So it will be OD plus OB. Now what is this OD plus OB? Isn't it the other diagonal BD? Yes, it is. So what we'll do is half AC will be written as it is AC and OB plus OD gives us the diagonal BD. So ultimately the formula for the area of the rhombus is half into diagonal 1 into diagonal 2. In short, we see that the area of the rhombus is half multiplied with the product of its diagonals. So if we have been given two diagonals to us, we can easily calculate the area of the rhombus. Now that I have taught you to calculate the area of a rhombus, let us try this problem. So in this problem, we have to calculate the area of the rhombus in which the length of the diagonals are given, that is 10 centimeters and 8.2 centimeters. So first of all, the formula for area of rhombus was, I think you all remember, that was half multiplied with D1, that is the length of the first diagonal, multiplied with D2, that is the length of the second diagonal. So this will be equal to half multiplied with 10 multiplied with 8.2 and the unit will be centimeters square. This 2 gets cancelled up with 8.2, leaving behind 4.1. Now 4.1 multiplied with 10 gives us 41. So ultimately the area of the rhombus is 41 centimeters square. In the previous lecture, I taught you that in case of a parallelogram, if we join any of the diagonal, then it will be dividing that parallelogram into two congruent triangles. So is it true for a trapezium as well? Let us check it. So here ABCD is a trapezium. Now we have joined this diagonal AC such that this diagonal AC divides this entire trapezium ABCD into two triangles. One is triangle ADC and the other is triangle ABC. Now let us check that whether these two triangles, that is triangle ADC and triangle ABC, are congruent or not. Now we know that in order to prove congruency, we need to have three criteria. So the first criteria over here for congruency is that angle 1 will be equal to angle 2. Angle 1 will be equal to angle 2. The reason behind is that they are alternate interior angles. So they are alternate interior angles. But the second point here we have is this common side. which is common to both the triangles. So I'll be writing AC is equal to AC. That is the common side. But for proving congruency, we need to have this third criteria for congruency. But in this two triangle, we don't have any third thing that proves congruency. So this third congruency condition is missing in case of a trapezium. But if we had a parallelogram, this third condition would have been satisfied, and thus the triangles that the parallelogram's diagonal divide was congruent. But in case of trapezium, the diagonal divides the trapezium into two triangles, but they are not congruent. So the answer will be no. The trapezium cannot be divided into two congruent triangles. It will be divided into two triangles, but those two triangles will not be congruent at all. Now let us try finding the area of these quadrilaterals that has been given to us. So first on the list is this quadrilateral ABCD. The diagonal AC has been joined such that it is divided into two triangles. Now in the previous lecture I taught you about the area of this quadrilateral in a much more simpler way. That was, to find the area, we have to use this formula, that is half into the common base of these two triangles, which is AC. So it will be AC multiplied with the sum of the perpendicular drawn from opposite vertices to this common base AC. So here this 3 is the height h1 and 5 is the height h2. So we'll add them up. That is 3 plus 5. So ultimately we have half. This common base AC has a length of 6 centimeters. So it will be 6 multiplied by 5 plus 3 gives us 8. So this is 3. And 8 multiplied with 3 gives us 24. So ultimately the area of this quadrilateral will be 24 centimeters square. Now the second figure that has been given to us is a rhombus, because all the sides are equal and the opposite sides are parallel to each other. So in case of a rhombus, I told you that the diagonals, they bisect each other. So if this length is 6 centimeter, this length will also be 6 centimeter. And if this length is 7 centimeter, this length will also be 7 centimeters. So ultimately the diagonals we get are of 12 centimeters and 7 plus 7, that is 14 centimeters. In order to calculate the area, the formula for the area of a rhombus is half multiplied with the product of the diagonals, that is d1 into d2. So here we have half multiplied with d1, diagonal 1 is 12 centimeters and diagonal 2 d2 is 7 plus 7, that is equal to 14 centimeters. 2 cancels up 14, leaving behind 7, and 12 multiplied with 7 gives us 84 centimeters square as the area of the given rhombus. The third figure given to us is a parallelogram. Now we know that the diagonal of the parallelogram divides the parallelogram into two congruent triangles of equal area. So in order to calculate the area of parallelogram ABCD, we can also write it as that the area of parallelogram ABCD is equal to 2 times the area of this triangle ABC, because it divides the parallelogram into two equal triangles. So if I calculate the area of one triangle, multiply it with 2, it will result in the area of the parallelogram. So it will be 2 times the area of triangle ABC. Now, for calculating the area of triangle ABC, the formula is half into base into height. The base of triangle ABC is AC, which is equal to 8 centimeters, and the height of triangle ABC is 2 centimeters. This 2 gets cancelled out with this 2. Leaving behind 8 multiplied with 2, that gives us 16 centimeters square as the area of the given parallelogram. Till now, we have been talking about quadrilaterals. Now, what if we get a polygon? If we get a polygon and we have to calculate the area, we need to divide it into such figures whose area is known. So over here, we have an example that ABCDE is a polygon and we have to calculate the area of this polygon. So in order to calculate the area of this polygon, we will divide this polygon into 3 parts by joining AC and AD. Now when we join AC and AD, we find that this polygon is divided into 3 triangles. One is ABC, the other is ACD and the other is ADC. If we sum up the area of these three individual triangles, that will result in the area of the polygon. So we can say that the area of the polygon ABCDE is equal to the area of triangle ABC plus area of triangle ACD plus area of triangle AED. In order to calculate the individual triangle area, we'll be using the formula that is quite simple: half multiplied with base multiplied with the corresponding height of the triangle. In this way, we'll be calculating the area of each of the individual triangles, add them up to get the area of the required polygon. Another polygon that we have been given over here is ABCDE. Now just observe the figure carefully. What we'll do is we will divide this polygon into four structures. Four geometrical shapes that are known to us, whose area's formula is known to us, so that we can easily calculate the area of the polygon. In order to do so, first of all, we'll join AD and then draw two perpendicular lines BF and CG, which is falling on this base AD, such that this entire polygon has been divided into four parts. The first one is this triangle ABF. The second one is this trapezium FGCB. The third is this another triangle, which is a right angle triangle GDC. And the fourth one is this bottom triangle, that is AED. In order to find the area of this entire polygon, we will sum up the area of each and every small structure that we have divided this polygon into. So area of the polygon will ultimately be the area of the right angle triangle AFB, that means this area of triangle, added up to the area of this trapezium BFGC, added up to the area of another right angle triangle, that is CGD, and then added up to the area of this bottom triangle, which is triangle AED. Adding up all of them results in the area of the given polygon. Now over here we have been given with two polygons, namely FGHIE, this is a polygon, and we have another polygon, that is NOPQRM, this is another polygon, where FI and NQ are the diagonals of the polygon. Now, in order to find the area of this entire polygon, we have to divide this polygon into some of the known geometrical shapes and then calculate the area. So let's do it. The first thing that we'll do is we'll draw a perpendicular from G falling on FI. Let us name it. Let us name it as X. Again, we'll draw another perpendicular from H falling on FI base and let us name as Y. So this is a perpendicular, so it will be making 90-degree angle. So this entire polygon has been divided into a triangle, a trapezium, another triangle and another bottom triangle. So the entire polygon has been divided into total four geometrical shapes. The first one is the right angle triangle FXG. The second one is a trapezium XYHG. The third one is a triangle, which is again a right angle triangle YIH. And another last one is the bottom triangle, which is FEI. If we add up the area of each of these shapes, that is 3 triangles and 1 trapezium, that will result in the area of the polygon. Now the next polygon we have over here is MNOPQR. Now NQ is the diagonal of this polygon. Let us draw a perpendicular from O point to this base and draw another perpendicular from P point to this base. Let us name them. Let us name as L and M. Again, what we have to do is to draw perpendiculars from M to the given base and then draw perpendicular from R to the given base as well. So if we draw the perpendicular from M and we draw the perpendicular from R, let us name it as O. Okay, O has already been named. M, and let us name it as J and K. So this is J and this is K. So what happens is that the entire polygon has been divided into 6 structures. What are these 6 structures? We have a first right angle triangle over here, that is NLO. We have a trapezium over here, that is LMPO. Another right angle triangle over here, that is MPQ. And then the same thing is there in the bottom as well. So in total, we have 4 right angle triangles and 2 trapeziums. If we add up the area of these 4 right angle triangles and these 2 trapeziums, we'll end up getting the area of the given polygon. Now look at the question given to us over here. So here we have a polygon ABCDE which has been divided into different parts as shown in this figure. So this entire polygon ABCDE has been divided into 4 parts, that is 2 right angle triangle, 1 trapezium and another triangle which is below it. So what we have to do is to calculate the area of this entire polygon. So the area of the polygon ABCD will be equal to the area of triangle ABF plus the area of trapezium FHCB plus area of triangle HDC, which is again a right angle triangle, added up with the area of triangle AED. So we will calculate the individual areas of these figures, these 4 figures, and then add them up to get the ultimate area of the polygon that has been given to us. So the area of this first triangle, that is AFB, will be equal to half into base into height, that is half into AF multiplied with FB. The area of the second figure, that is the trapezium, will be equal to half into sum of parallel sides into the perpendicular distance between them. So it will be half, the sum of parallel sides is BF and CH. So it will be BF plus CH multiplied by the perpendicular distance between them, that is FH. Now talking about the next right angle triangle, we have the area is half multiplied with base, that is HD, multiplied with the height, that is CH. And then lastly, we have another triangle below it, that is area of triangle AED. In order to calculate this area, we will use the formula half into base into height. That is half into base, entire base, that is AD, multiplied by the height over here given is GE or EG, as you feel like. Just name it GE. So what we have to do is to put the values of these terms in this thing in order to get the area. So first of all, we'll write half in place of AF. The length of AF has been given to us in the question, that is 3 centimeters. So I have written 3. Now multiplied with BF. The length of BF has also been mentioned in the question, that is 2 centimeters. So I have written half into 3 into 2. Now next thing is the area of the trapezium, which is equal to half into the sum of parallel sides BF and CH. BF is 2 centimeters and CH is 3 centimeters. So it will be half 2 plus 3 multiplied by the perpendicular distance between them, which is equal to FH. Now FH has not been directly given into the question, so we can calculate FH using the formula AH minus AF, because FH is this whole AH minus AF. AH has been given in the question, that is 6, and AF has also been given as 3. So FH will be 6 minus 3, which is equal to 3 centimeters. So the value of FH, that is the perpendicular distance, has been put in the formula of the trapezium. Next up, we have again another right angle triangle. So to calculate the area of this right angle triangle, we have to take half into base HD into the height CH. So base HD is 2 centimeters and the height is 3 centimeters. Now again, HD was not directly given into the question. So what we did was, we took HD is equal to AD minus AH. AD is 8 centimeters and AH is 6 centimeters. So ultimately this will result in 2 centimeters HD. So we have put the value of HD as 2 centimeters and CH as 3 centimeters. Next up, we have a triangle in the bottom side. So the area of this triangle will be half into the base of this triangle, that is AD, which is equal to 8 centimeters, and the height of this triangle, that is GE, which has been given in the question as 2.5 centimeters. So I wrote 8 into 2.5. Now let's solve this. So what will I do is, I'll cancel up this 2 and 2. So the term that is remaining in the first area of this triangle is 3. Over here we have 3 plus 2 gives us 5. 5 multiplied with 3 gives us 15 divided by 2. 15 divided by 2 gives us 7.5. Over here again this 2 will get cancelled out with this 2, leaving behind 3 from the next term. That is the area of this triangle. And the area of this bottom triangle will be equal to half into 8 into 2.5. This 2 will get cancelled out with 8, leaving behind 4. 4 multiplied with 2.5 gives us 10. Now when we add these four things up, that is 3 plus 7.5 plus 3 plus 10, this results in 23.5. So I can see 23.5 is the required area of the given polygon, and the unit will be in centimeters square because each of the length has been given in centimeters. Now we have another similar problem in which there is a polygon, that is MNOPQR, and it has been divided by joining the diagonals and drawing perpendicular from the opposite vertices. So here MP is the diagonal of this polygon, NAOC, RB and DQ are the perpendicular that has been drawn on the diagonal. So we have been told to calculate the area of this entire polygon. So in order to calculate the area of the polygon, we have to calculate the area of this triangle MAN. Then we have to calculate the area of the trapezium ACON. Then the area of another right angle triangle, that is CPO. Then the area of another triangle, that is MBR, followed by the area of a trapezium BRQD and the area of this triangle DQP. So ultimately, when we add all of these areas, we'll get the area of the polygon, because the polygon is made up of all these areas. There are ultimately 6 figures. We have 4 right angle triangles and 2 trapezium. So if we add up all the areas, we'll end up getting the area of the polygon. So first up, we have the area of this triangle, that is MAN. It will be half into base MA into height NA. Talking about the area of the next figure, that is the trapezium ACON, it will be half into the sum of the parallel sides into the perpendicular distance between them, that is half into NA multiplied plus OC multiplied by the perpendicular distance between them, that is AC. The next up, we have the third triangle, that is triangle CPO. It is a right angle triangle, so its area will be half into base into height, that is half multiplied with CP multiplied with OC. Next up, we have another right angle triangle, that is triangle MBR. Its area will be half base, that is MB, multiplied with height, that is BR. Next up, we have another trapezium whose area will be half into the sum of its parallel sides, that is BR plus DQ, multiplied by the perpendicular distance between them, that is BD. The last thing that we have over here is another right angle triangle, that is DQP, whose area will be half into base, that is DP, multiplied by the height DQ. So we'll calculate it. We'll be putting the values of each and everything in this given equation to find out the area of the given polygon. So I write half multiplied by MA is 2. And then we have to multiply NA, which is the height of the triangle, which is also 2.5 centimeters. So I've multiplied half into 2 into 2.5. This entire thing gives us the area of the first triangle. For the area of the trapezium, we have half multiplied with NA plus OC plus multiplied with AC. So NA and OC are 2.5 and 3 centimeters respectively. So I've added up 2.5 and 3 and then multiplied with AC. Now AC is not directly given into the question, so we can calculate AC using the formula AC is equal to MC minus of MA. MC is 6 and MA is 2. Ultimately AC gives us 4 centimeters. So we'll put the value of AC in this area of trapezium. So half into 2.5 plus 3 into 4 gives us the area of the trapezium. Next up, for the area of this triangle CPO, we have half into base CP. Base CP is not given directly, so we have to calculate the base CP. We can use MP minus MC. This MP minus MC will give us the base CP, which is 9 minus 6, that is 3. And then we have to multiply it with the height OC, that is again 3. So half into 3 into 3 is the area of the next triangle. Now we have to add up the area of this bottom triangle, that is MBR. For this we have to write half into base MB. Now base MB has been given in the question as 4 centimeters. So I have written half multiplied with 4. Now it has to be multiplied with the height, that is BR, which is 2.5 centimeters. So half into 4 into 2.5 centimeters gives us the area of the next triangle. Now half into 2.5 plus 2 into 3, this is actually the area of the next trapezium, that is BRQD. Half into the sum of the parallel sides, that is 2.5 plus 2, multiplied with the perpendicular distance BD between them. Now BD has not been directly given into the question, so we'll be calculating BD by using this formula, that BD is equal to MD minus of MB. So when we do this, MD minus MB, this is 7 minus 4, which gives us 3. So we'll put the value of BD is equal to 3 in the area of trapezium, and thus we get this as the area of trapezium. Next up, we have the last thing, that is the triangle DQP as a right angle triangle whose area will be half into base DP multiplied with height dq. dq is 2 centimeters, but base dp is not directly given in the question. So what we will do is we will take mp minus md, which will give us dp, which is 9 minus 7, that is 2. So we have put 2 centimeters in the formula. Now let's calculate the individual areas, add them up to ultimately get the area of the polygon. So this 2 will get cancelled up with 2 and we'll be left with 2.5. Now over here, this 2 will get cancelled up with this 2, this 4. Leaving behind 2, we have 2.4, 2.5 plus 3. This is 5.5. When 5.5 is multiplied with 2, it results in 11. Now, over here, we have 3 multiplied with 3. That gives us 9. 9 divided by 2 gives us 4.5. Plus, next we have over here is half multiplied with 4 multiplied with 2.5. So this 2 will get cancelled up with this 4, leaving behind 2. 2 multiplied with 2.5 gives us 5. Next we have this area of trapezium, that is half 2.5 plus 2 into 3. 2.5 plus 2 gives us 4.5, and when we multiply it with 3 and then divide it with 2, it will ultimately result in 6.75. I think you can all calculate it. It's just a simple calculation. 2.5 plus 2 gives us 4.5. We will multiply it with 3 and then divide it with 2. It will give us 6.75. And then over here, 2 and 2 gets cancelled up. So the last area of this triangle DQP is 2 centimeters. When we add all of them up, that is 2.5 plus 11 plus 4.5 plus 5 plus 6.75 plus 2, we end up getting 31.75 centimeters square as the area of the given polygon that is MNOPQR. In the previous lecture, I taught you how to calculate the area of the trapezium. I hope you all remember the formula. The formula was half multiplied with the sum of the parallel sides multiplied with the perpendicular distance between them. So here we have an example, that is, the area of the trapezium shaped field is 480 meters square. The distance between the two parallel sides is 15 meter. If one of the parallel side is 20 meter, find the other parallel side. So first of all, we will write the given things in the question. The given stuffs are area is 480 meters. The height is 15 meters. Height is actually the perpendicular distance between the two parallel sides. We represent it by h. And then one of the parallel side has been given as 20. And what we need to find out is the other parallel side. So let us take the other parallel sides as x meters. Now let us put the formula of area. Area of trapezium. The formula was half multiplied with the sum of the parallel sides. Now one parallel side that has been given in the question is 20 and the other parallel side that we have assumed is x. So half into 20 plus x multiplied by the perpendicular distance between the parallel sides, which has been given in the question as 15 meters. So it will be 15. Now this entire thing is actually the area of the trapezium, because the formula is of area of trapezium, but we have been given in the question that the area of trapezium is 480 meters square. So ultimately this entire thing will be equal to 480. So we'll solve this linear equation. Now what will be over here? We'll take this 2 and 15 on the right hand side. So on the left hand side we are left with 20 plus x is equal to 480 multiplied with 2, and 15 is in the numerator side of the left hand side. So when it comes to RHS, it will go in the denominator. Now 15 will cancel up with 480 and it will result in 32. 32 times 480. Now when we multiply 32 with 2, it gives us 64. So ultimately we have x is equal to 64 minus of 20, which gives us 44 meters. So we can say that the length of the other parallel side is 44 centimeters. So we can conclude that length of other parallel side will be equal to 44 meters. I hope it's clear. Now let's try solving another question. But over here, the figure that has been given is a rhombus. So the question is, the area of a rhombus is 240 centimeters square. One of the diagonal is 16 centimeters. Find the other diagonal. So we know that the area of a rhombus is half into product of its diagonals. So we have been given one diagonal D1 as 16 centimeters and the area is 240 centimeters. We have to calculate the other diagonal, that is D2. So according to the problem, we know that the area of the rhombus is half multiplied with the product of the diagonal, that is D1 into D2. This gives us the area. So we'll be putting the value of area and diagonal D1 in this equation. That is half multiplied with diagonal 1 is 16 centimeters and diagonal 2 is unknown. We have to find this diagonal. So I'll be simply writing as D2 is equal to the area of the rhombus, which is equal to 240 centimeters square. So I wrote 240. Now D2, in order to calculate D2, we have to take 16 and 2 towards the right hand side. So I took 16 in the right hand side, so it came to the denominator and 2 came to the numerator. Now when I cancel up 16 with 240, it gives me 15. 15 multiplied with 2 gives me 30. So I can say that the other diagonal of this rhombus will be 30 centimeters. Now let's come to the next problem. Here we have a hexagon MNOPQR in which each of the sides is 5 centimeters. So hexagon is a 6-sided figure and each of the sides is 5 centimeters. So it will be a regular hexagon. Now there are two people. One is Aman and other is Riddhima. They tried to find out the area of this hexagon in two different ways. Aman divided this hexagon into two equal trapeziums. And what Riddhima did was, she joined this BC and AB of this hexagon such that this hexagon was divided into three parts. One is the rectangle and other two are the triangles. So let us try finding out Aman's method of calculating the area of trapezium and Riddhima's method of calculating the area of trapezium. So in Aman's method, the area of the entire polygon will be equal to 2 times the area of the trapezium NMR cube. Because when we divide this diagonal, then the hexagon gets divided into two equal trapeziums. So I'll be writing 2 times the area of trapezium. Now the area of trapezium is half multiplied with the sum of the parallel sides, that is MR plus NQ, multiplied with the perpendicular distance between them, that is MA. Now MA has not been directly mentioned, so we have been given this entire length, that is MO as 8 centimeters. So MA will be half of MO, so it will be 4 centimeters. Now what I have to do is to put the values. So here I have this 2 will get cancelled out with this 2. I have MR plus NQ. So MR gives me 5 plus NQ given is 11. So 5 plus 11 multiplied with MA. MA is 4 centimeters. So ultimately we have 11 plus 5, that is 16, multiplied with 4. This gives us 64 centimeters square as the area of this given hexagon according to Aman's method. Now let us look at Riddhima's approach. So what Riddhima did, she divided this entire hexagon into 3 parts. So in order to find out the area of this hexagon, we have to add up the area of these two triangles along with the area of the rectangle. So area of the trapezium will be equal to the area of rectangle ABCD plus area of triangle DEC plus area of triangle ABF. Now the area of rectangle ABCD will be length into breadth, that is AB multiplied with AD, and the area of these two triangles will be half into base into height. For this triangle we have half into base BC multiplied with the height EG, and for the bottom triangle again we have half multiplied with base AB multiplied with the height, that is FH. Now the height was not directly mentioned in the question. This entire height was mentioned. This entire distance was mentioned as 11 and this AB is, this AD portion is 5. So we'll subtract 11 from 5, we get 6. That means 6 is evenly distributed in the top and the bottom portion of the rectangle. So height of each of the triangles will be 3 centimeters. 11 minus 5 gives us 6. 6 is evenly distributed in the top and the bottom portion. So it will give us 3 as the height of each of the rectangles. Now let us put the values. Over here, AB over here will be 8 and AD, that is the breadth of the rectangle, is 5. So 5 multiplied by 8 gives us the area of this rectangle. Now we'll calculate the area of the triangle which is on top of the rectangle. That is area of triangle DEC. For that we have half multiplied with DC. DC is actually 8 centimeters. Multiplied with EG, which is the height, and it is 3 centimeters. Plus we have to calculate the area of the bottom triangle. That is area of triangle AFB, which will be equal to half multiplied with base AB, that is again 8, and height FG, which is 3 centimeters. 8 multiplied with 5 gives us 40. This 2 will get cancelled out with this 8 and result in 4. And again this 2 will get cancelled out with 8 and result in 4. 4 multiplied with 3 gives us 12. And again 4 multiplied with 3 gives us 12. So ultimately we have 40 plus 12 plus 12 gives us 24. So this will be equal to 64 centimeter square. So from here we can conclude that Aman and Ritima both tried different approaches, but ultimately they got the same area, that is equal to 64 centimeters square. So whatever approach you try, your approach should be proper and the answer of the area will always be the same. Now we will be discussing about solid shapes. So solid shapes are those shapes that occupies a specific volume and they are three-dimensional space. So the examples of solid shapes are a cuboid. It occupies some space and at the same time it is a three-dimensional shape. So it is a solid shape. Next up we have a cube. We also have a cylinder, a cone and a pyramid. So all these shapes are known as solid shapes. Now we also know that a solid shape has three things: vertex, base and edge. So here this point, the meeting point of the edges, they are known as the vertex, and then faces are the flat surfaces that makes up the solids, and then talking about the edges, these are the line segments that joins the faces. So in a solid shape we have these three things: vertex, faces and edges. The first solid shape that we have over here is a cuboid. So in a cuboid, what happens is that there are total 6 faces in a cuboid and all these faces are rectangular shape. And the other criteria of a cuboid is that all these faces will be rectangular, and second thing is that the opposite faces will be identical to each other. You take a rectangular box and then observe. There will be in total 6 faces in this cuboidal box, and then the opposite faces, that is the top and the bottom, it will be identical. These two side faces will be identical and these back and the front face will be identical. So in total we can say that we have 3 pairs of identical faces in a cuboid. So there are in total 3 pairs of identical faces in a cuboid. The next solid shape that we have over here is a cube. Let us take a cubical box. What is it made up of? A cubical box will be made up of 6 identical square faces. In a cube, each of the face is a square and each of the face will be identical to the other 5 faces. So we can say a cuboidal box or simply a cubical box or simply a cube is made up of 6 identical square faces. Now we'll talk about cylinder. So a cylinder is also a solid shape which consists of a curved surface and 2 identical circular faces, one on the top and the other on the bottom. So what happens is that when we have a curved surface and then 2 identical circular faces, one on the top, other on the bottom, then that results in the formation of a cylinder. So the most important point in a cylinder is that the top and the bottom faces should be circular and that should be identical. The circular base of top and bottom are identical. Now that we have talked about cylinder, let us talk about a specific case of a cylinder, that is right circular cylinder. Now in case of a right circular cylinder, what happens is that there are 2 circular faces, one is at the bottom, other is at the top. So in case of right circular cylinder, these 2 faces, the top circular face and the bottom circular face, will be parallel to each other such that the line joining the center of these 2 circles will be perpendicular to the base of the cylinder. So such a cylinder will be known as a right circular cylinder. So here a figure of a right circular cylinder has been given where the top circular portion and the bottom circular portion are parallel to each other, and the line joining the center of these two circles are perpendicular to each of the bases. It is perpendicular to the top base, that is, it is making an angle of 90 degree with the top base, and this line which is joining the center of both the circle is also perpendicular, that is making an angle of 90 degree with the bottom circular base as well. So this will be known as a right circular cylinder. And over here another example is given. This is also a cylinder, but why it is not a right circular cylinder? Because the angle between these two faces, that means the angle that this line joining the center of the circle that is making with the base is not 90 degree. It is not equal to 90 degree. That is why we can say that this is not a right circular cylinder, because for a right circular cylinder, the angle that the line joining the center of the circle should be equal to 90 degree. Should be equal to 90 degree. That means this line should make an angle of 90 degree with the bases of the cylinder. Now observe the figure given over here. It has been told that why is it incorrect to call this figure a cylinder? First of all, in case of cylinder, I taught you two main criteria. The first criteria was that there should be two identical circular faces in a cylinder. In this cylinder, there are two circular faces. One is at the top, other is at the bottom. But these two circular faces, are they identical? No, they are not identical. So we can say that just because these two circular faces of the top and the bottom, they are not identical, so calling this figure a cylinder will not be proper. Though this figure is satisfying the second criteria, that the two circular bases are parallel to each other and the angle that this line joining the center making with the base of the cylinder is 90 degree. But the first criteria, that these two circular bases should be identical, is not satisfied. That is why we can say that this figure is not a cylinder.